Okay, hello. Um, Today I'm going to be talking about the topology on the real numbers. Um, and so what I'm going to do here in this analysis series is present real analysis in terms of topology, right? So I have, the topology series, and um, I've noticed a lot of times in colleges, it's often the other way around. Analysis is taught sort of before topology, um, like you're expected to know analysis before you take topology, and um, it's sort of a driving motivation for topology. However, I don't like this viewpoint because, for one, you end up spending a lot of time in analysis going over topology just to sort of do it all again, but more generally in topology. And I think that's kind of a waste of time. Covering topology by itself before doing analysis makes analysis less tedious, right? You can generalize arguments using results you've already proved, and of course, if you go into higher mathematics, you're going to need that topology anyway. So I think it's a better viewpoint. Um, of course, this might come as an inconvenience to someone who is watching and let's say they're studying for an analysis course and they don't have a topology background. So of course this wouldn't be for you, and I apologize about that, but I believe this is the best way to approach real analysis. So without further ado, let's talk about the topology on R, right? And so I'll briefly remind you what a topology is, right? So a topology is defined on any set, or it can be defined on any set. So let's say you start with the set S, has a collection of subsets, and so I denote it by T. I mean, this is sort of like a tau, but this doesn't really matter, such that three properties hold. So the first one is that the empty set and the whole set are elements of this collection, right? The second property is that if U1 and U2 are elements of the collection, then the intersection must also be in this collection. The third property is that if some collection of these sets, right, some subcollection where then the union of all these sets is also in the collection, right? So 2 is saying that if you take finite intersections, you're still in the collection. But 3 is saying you can take arbitrarily many unions. So this is a stronger condition, but it's only for unions. Then T is a topology on S, right? And the elements of a topology are called an open set, right? And so that's just the basic definitions, right? And of course, like I said, I'm going to sort of assume that you've watched the topology series. So if you'll remember, there's also something called a basis, right? And a basis for a topology is essentially it's a collection of subsets such that here there's only two properties. One, any element of S has some, if I pick a point in S, I can find a basis element that contains it, right? That's the first condition. The second condition is that if B1 and B2 are in B, and P is in the intersection, there is B3, another basis element, such that P is in B3, and B3 is contained in the intersection. And a basis sort of defines a topology, right? The basis elements are open, and any open set can be expressed as a union of basis elements. And so we're actually going to use this idea to define the topology on R. Given by the basis of open intervals A to B, right? And that's pretty much it, right? So any open set is therefore a union of open intervals. So yeah. Notice we could also make this sort of more symmetric and call this, say the intervals are x minus r to x plus r, and these are identifiable with open balls of radius r at x, right? Of course, any open interval can be expressed like this, right? Where x would be a plus b over 2, and r is b minus a over 2. So these are equivalent ideas. So essentially, if P is an element of an open set, then that means there is an R greater than 0 such that P minus R, comma P plus R is contained in the open set. That's another way of thinking about the topology on R, right? Our open sets are sets such that whenever I have a point, I can find some ball around that point that's contained in the open set. So now that we have a topology on R, right, we can think back to the last episode of the topology where we had our metric spaces, right? And remember, metric spaces were sort of defined using R, which I sort of mentioned that, like, which was kind of like a little jump ahead, right? It's sort of assuming that you already had some idea of what the real numbers are, right? Now, of course, we can now that we have an idea of what R is, we can also define R as a metric space, is a metric space using the metric function is going to be defined as the absolute value of the distance, or of the difference, I should say, the absolute value of the difference between two real numbers, right? So this is just another way of thinking about R, right? And of course, when in the discussion of metric spaces, that's where we used the notation of B sub R of X, right? This is the set of Y in our space such that the distance between X and Y is less than R, right? And this is equivalent to X minus R and X plus R, which is a good exercise to check this, right? The next thing that I'm going to do in this video is talk about well, first let me say that we showed previously that when you have a metric space, then a compact set is closed and bounded, right? And so let me just talk about these definitions again, right? A compact set means that if you have, let's say C is compact, if you have some collection of open sets such that C is contained in the union, then that means we can find some finite subcollection such that C is contained in this finite union, right? And so I should say in a metric space. And so the reason it's bounded is because, and so bounded means that C is contained in some ball of radius x. The reason that a compact set is bounded in a metric space is because you can take the union of over the natural numbers of balls of radius n, right? So a ball of radius 1, ball of radius 2, and so on and so forth, right? And this follows from the Archimedean property, right? For y and c, d of xy is a real number. So there is a natural number such that d of xy is less than n, and this means that y is in the ball of radius n at x. So that's why it's bounded. Now closed set is the complement of an open set. And so the reason that a compact set in a metric space is closed actually, let me think of this. Uh, this is actually blanking me. Well, okay, so let's think. So the complement, so we want to show the complement of C is open, right? So let's say X is our metric space, C. So let's let P be a point. Then let's go check out be over here. Did I not prove it was closed? Oh, it might be a property of T2 spaces. Yeah, it's a property of T2. So a metric space is T2, right? And as a refresher, T2 means that for two different points, I can find open sets around them that are disjoint. And so, or is it XBT2? Yeah, I remember. Okay, so the idea is that, so the reason why a metric space is T2, right, is that if I have 2 points, they have some distance, and so I can take balls of radius half that distance, and they are disjoint open sets, right? Now, I can take some point outside my compact set, and I can find a covering given by basically taking each point in the set and finding some pair of open balls around the point and around the point outside the set and around the point in the set, such that they're disjoint. And then that will form a covering, and then I can find a finite covering, and if I union those, I get some open set, and if I intersect them around the point P, I also get an open set because they're finite, and therefore I get some open set around P, which is contained completely in the complement around A. So the complement is open, and therefore A is closed. So sorry for that sidetrack. So I probably should make this into a second video because that was not good. Right. Anyway, right. So, right, we previously proved that in a metric space, a compact set is closed and bounded. And so what we are going to do is that, and I was going to do it in this video, but I'm probably just going to make it a separate video, is show that in the real numbers, compactness is equivalent to closed and bounded. Right? So we already have one direction, right? We already know that a compact set is closed and bounded because R is a metric space. Oh, excuse me. So in the next video, we are going to prove, and this is called the Heine-Borel theorem. So in the next video, we are going to show that a closed and bounded set is compact. So yeah, I'll see you then.